So who is Albert Einstein? The creator of special and general theories of relativity was a German mathematician and scientist named Albert Einstein. He was awarded the Nobel Prize in Physics in 1921 for his description of the photoelectric phenomenon. The German Nazi Party targeted him, and in a decade that followed, he immigrated to the United States. Additionally, the advancement of atomic energy was significantly influenced by his work. The study of integrated field theory was Einstein's later area of interest. At the age of 76, he passed away in April 1955. We can all agree that Einstein was the most important physicist in 20th century because of his curiosity. Theory of relativity. Einstein's theory of relativity, proposed in 1905 and expounded upon 1915, revolutionized physics by connecting space and time into a unified structure known as the space-time. So this theory, which accounted for gravity's effect on space-time, enhanced prediction of planetary orbits and offered a deeper understanding of gravitational forces. Despite initially rejecting the idea of an expanding universe, Einstein's work was later validated, including by observations during 1990 solar eclipse and subsequent discoveries such as the Hubble's confirmation of cosmic expansion, modern experiments like those tracking stars S2 near a black hole, and continue to affirm aspects of Einstein theory, underscoring its enduring relevance in scientific exploration.
The general relativity. Back in 1915, Albert Einstein proposed a general relativity that changed the way we understand gravity by not depicting it as a force acting at a distance like in Newtonian physics, but spacetime's curvature occurs because of the presence of a mass and energy. A physical theory that deals with space and time is also known as general relativity. The Einstein equation is the equation that explains how the matter curves spacetime according to general relativity, which defines it as a four-dimensional object. The gravitational field is created through general relativity's description of a curved spacetime. This curvature affects the movement of objects, including the trajectory of light and the behavior of massive bodies. Mass and energy causes the fabric of spacetime to curve, which lead to a phenomenon such as a gravitational lensing, gravitational attraction, and also the formation of black holes. Numerous experiments and observations have confirmed and tested this theory, leading to a profound understanding of fundamental nature of gravity. And now, let's move on to the experimental confirmations. Einstein theories of relativity have been tested and validated through various experiments and observations over the years. And this too here is the best or mostly known experimental confirmation for special relativity. Prior to Einstein theory, the Michelson-Morley experiment laid the foundation for a special relativity. It aimed to detect the ether, a medium believed to occupy space and transmit light waves. The experiment demonstrated that light travels at a constant pace in all inertial reference frames. It is a contradiction of the classical concepts of space and time and opening the door to special relativity. So now, next is the global positioning system. The accuracy of this system is based on addressing the time dilation effects predicted by special relativity. Time dilation occurs when the GPS satellites orbit Earth at a high speeds relative to observers on the ground. Without special relativity corrections, our GPS systems would quickly become unreliable. And now, here's the best two or mostly known experimental confirmations for general relativity. Einstein's theory of general relativity is mostly popularly validated through Eddington's solar eclipse expedition. After the publication of general relativity in 1915, Arthur Eddington, an English astronomer, organized an expedition to observe how stars were positioned near the sun in the midst of a solar eclipse. The curvature of spacetime by massive objects was confirmed by the observed bending of starlight due to the sun's gravitational field, according to Einstein's theory. And now, next is the bending of starlight by massive objects. There is now one that validates the theory of general relativity apart from the Eddington expedition, as numerous observations of gravitational lensing have confirmed that bending of light by massive objects like galaxies and galaxy clusters. Not only does this effect validate general relativity but also assist astronomers in studying the distribution of the dark matter in our universe. These experiments and observations confirm the validity of Einstein's theories of relativity, which reinforce his significant contributions to our understanding of gravity and the nature of spacetime.
For technological application, Einstein's theory have done wonders. It is very important for the precision of GPS technology that we correct for time dilation in light of Einstein's predictions, since this guarantees precise worldwide navigation. Moreover, the realization of Einstein's prediction about gravitational waves resulted in more sophisticated equipment like LIGO. These detectors expose never before seen aspects of cosmos. What they do is provide an unprecedented detailed view into cosmic events such as the supernovae or black hole mergers, thereby laying bare some hidden corners of space. For example, by detecting gravitational waves for the first time ever in 2015, LIGO made a historic discovery that confirmed their existence and thus marked one of the greatest breakthroughs, both in physics and astronomy, at large-scale measure. Scientists can now use Einstein's theory to probe into depths of space that were unimaginable before, thereby creating new opportunities for understanding the essence behind this fundamental property. Space itself being nothing but a fabric woven by time and gravity as it is needed.
First, we have ethical implications. These ethical implications emerge when several seeming changes become impossible to achieve without creating atomic weapons to win World War II. This concern about scientists' responsibility and the potential consequences of scientific discoveries is important. Second, cultural icon. Einstein's philosophy and lifelong pursuit of social justice and peace have become a great asset in the discussions about the place of science in society. Lastly, technological advances. Several technological advances, including satellite, communications, GPS systems, and medical imaging, can trace their origins to Einstein's work. They have transferred contemporary life and altered the ways humans interact with the outer world.
For unsolved mystery and future direction, Einstein's theory have led to investigation about dark matter, dark energy, how gravity joins with other forces, and the search for a full theory of quantum gravity. One such idea is the dark dimension, which postulates that within string theory there could be an extra dimension where dark gravitation produces heat. This dimension makes up dark matter. This proposal connects string theory with quantum gravity, particle physics, and cosmology by providing a single framework for addressing foundational questions about nature. Not testable yet, but able to make predictions that can be verified through lab experiment or astronomical observation. The dark dimension scenario suggested here has recently some support from observation, though there remains skepticism among certain physicists. However, even if it were not proven true, still the concept would serve as a fruitful way forward in terms of understanding what makes up most of our universe according to Einstein's theory. Those strange things that hide their workings from us while being governed by them. Whatever.
Albert Einstein's seminal contributions transferred physics and our perceptions of the cosmos.
The following outline his principal theories and contributions. Quantum theory. While relativity is Einstein's most famous field of study, quantum theory also benefited greatly from his work. He disagreed with the accepted understanding of quantum physics and famously argued against the theory's probabilistic basis by saying, God does not play dice. Nevertheless, his observations and critics influenced the advancement of quantum mechanics. Brownian motion, 1905. The Brownian motion, the random motion of particles suspended in fluid, was theoretically explained by Einstein. He provided compelling proof for the existence of atoms and molecules by demonstrating that the motion is brought about by the fluid's molecules colliding with the particles. Photoelectric effect, 1905. The photoelectric effect, which occurs when a material is exposed to light and releases electrons, was described by Einstein. He postulated that photons, which are discrete packets of energy, make up light, and that energy of these photons control how the electrons in a material behave.